Hello everyone, and welcome to Biopedia. The renowned scientist James Lovelock died on the 26th of July 2022 on the day of his 103rd birthday. I think it's fair to say that Lovelock was one of the bigger names in popular biology, and certainly that the Gaia hypothesis is reasonably well known. As a tribute of sorts, this episode is going to outline Lovelock's life and some of his achievements, as well as touch on two areas of his academic career which I've had some interaction with: his 1965 paper on how to detect life on Mars, and the Gaia hypothesis. What I will say at the start of our discussion is that this is not an episode on the Gaia hypothesis itself. I am only scratching the surface here, in the form of Lovelock's own work and some summaries of the reaction to its publication. I aim to come back to this topic in one or more episodes and give it the attention it deserves. Moreover, this will be more of a skip through Lovelock's life rather than a detailed examination for obvious reasons. With that said, let's get to it. James Ephraim Lovelock was born on the 26th of July 1919 as the child of Thomas Arthur Lovelock and Nellie Ann Elizabeth March. He became interested in science as a child from reading Jules Verne and H.G. Wells, notable for such works as 20,000 Leagues Under the Sea and The War of the Worlds respectively. His parents couldn't afford to send him to university, so he worked as an industrial lab technician, working on his degree through classes in the evening. He would get a degree in chemistry in 1941 from the University of Manchester. During the next 20 years, he would work at the National Institute for Medical Research, also working at Salisbury's Harvard Hospital from 1946 to 1951. In 1948, he received a PhD from the London School of Hygiene and Tropical Medicine. Between 1954 and 1955, he worked at Harvard University on cryopreservation, or preserving living matter at -196 degrees, often done by keeping it in liquid nitrogen. He would focus on gas chromatography at Yale between 1958 and 1959. Lovelock came up with ways to reversibly cool tissues and entire organisms such as hamsters. Also, as a brief aside here, in 1954 he cooked a potato using microwaves inside a device called a magnetron, which he wrote on his website might well have been the first ever successful use of the device we now call a microwave. Anyway, in 1957 he created a machine called the Electron Capture Detector, or ECD, which is employed in gas chromatography to detect traces of substances in samples. The device has subsequently been used to pick up small quantities of atmospheric halogenic compounds, as well as those same compounds in foodstuffs. These substances included DDT, a possibly carcinogenic pesticide whose usage was outlawed in the United States in 1972. Lovelock became a Doctor of Science in 1959, receiving his doctorate from the University of London, where he worked on biophysics. Between 1961 and 1964, he was a professor at the Baylor University College of Medicine in Houston in Texas. In this period, he collaborated with members of NASA, the National Aeronautical Space Agency, to create instruments for missions such as the Viking spacecraft. Lovelock described his involvement with space missions in a video interview uploaded to YouTube in 2017. He would commute to California every month to work with the Jet Propulsion Laboratory. He slowly became interested in the biological aspect of Martian life detection which was being worked on at the time. Lovelock noted that the goals for this life detection program were not realistic, as they assumed Earth-like life such as that found in the close-by Mojave Desert. Accordingly, he felt a more generic experimental approach was necessary. A leading figure in the project asked him what he proposed as an alternative, and Lovelock requested 3 days to think about it. He thought up a suite of experiments and suggested that the best way would be to study the atmospheric makeup of the red planet. He was told to return home and submit a report. This report was also submitted as a paper for the journal Nature and was published in 1965. So, let's have a look at how Lovelock argued you could detect life on other planets. Lovelock's argument was that a planet which had life was noticeably different from one which did not, in that order was abundant and there were things taking place on the planet which you wouldn't expect purely based on probability and the laws of thermodynamics. Order in this instance refers to orderliness in terms of chemical makeup or chemicals present. An example he refers to is the hydrocarbons present in sheep's wool which have between 11 and 33 carbon atoms in them. In an inorganic substance, you see what's known as a Poisson distribution in terms of hydrocarbon length. Think of this as what you'd expect to see when all the chemicals are in equilibrium with one another. By contrast, sheep wool differs from this, and, at larger molecular weights, you see a switching abundance as you get to larger molecules. To take a random example to illustrate this point, 10 carbon chains are abundant, 11 carbon chains are not, 12 carbon chains are, and so on. Lovelock also recommended searching for this same order in acoustic data. He doesn't mention this in his article, but an example would be the work that SETI, or the Search for Extraterrestrial Intelligence, were doing hunting for signs of off-planet life in, for example, radio waves. Finally, he argued that you could look for signs of a lack of chemical equilibrium on the planet. Just like we talked about with the sheep's wool example earlier, there's a certain deviation from what you would expect chemically when it comes to life. An example he notes is that our own atmosphere has both oxygen and hydrocarbons in it. As we know, oxygen is produced by photosynthesis. Now, an example of a reaction you would expect between oxygen and hydrocarbons would be oxygen and methane reacting to form carbon dioxide and water. So, just to go back to his point, both oxygen and hydrocarbons being present in the atmosphere could indicate life. But back to Lovelock's own life story. He was a visiting professor at the University of Houston from 1964 to 1974 and at Reading between 1964 and 1989. During this time, he came up with the theory that he is most famous for, the Gaia hypothesis. This would subsequently be refined with Lynn Margulis, herself best known as the primary architect of the endosymbiont theory, in the latter days of the 1960s and the 1970s before publication in 1979. The endosymbiont theory is another one of those topics that warrants discussion in a future episode, but as a quick primer, because it's been mentioned here, the basic idea is that both the mitochondrion and the chloroplast started out as free-living organisms and were engulfed by an ancestor of eukaryotic cells. The two organisms developed a symbiotic relationship and ultimately became two components of a single cell. If you want to play the game of how many connections between famous scientists you can make, Margulis was also married to the astronomer Carl Sagan. As we discussed earlier, I'm going to be relying on general outlines in terms of the Gaia hypothesis and the reaction to it, as it's only part of today's discussion and warrants more attention at a later date. Lovelock himself described the biosphere as the 3D space in which organisms existed, which contrasts with Gaia itself, a superorganism which the biota of the entire planet was a part of, as well as the Earth's atmosphere, water, and rock on the surface which life interacted with. He noted that how Gaia related to the biosphere was like how people related to their bodies. Put another way, the theory holds that Earth's biota forms a superorganism controlling the Earth's surface and atmospheric processes. In essence, life as a whole acts to sustain itself. There was initially resistance to this idea. It rubbed thinkers such as Richard Dawkins up the wrong way, with Dawkins viewing it as arguing against Darwinian natural selection. However, it has since been more widely accepted since Lovelock published further books on the subject in 1988 and 1991. Opponents initially believed that Gaia was being depicted in the first book as a being with agency and foresight, with the latter works more obviously portraying Gaia as a metaphor for Earth being a unit which organizes itself. The advantages of Gaia, in that it summarizes the complexity of how organisms interact and what the response to anthropogenic activity might be, have been noted. Gaia was essentially vindicated at a conference in Amsterdam in 2001, where over 1,000 scientists supported the idea of our planet as an entity which regulates itself. Lovelock continued writing, publishing The Vanishing Face of Gaia, The Final Warning, in 2009, which stated that billions would perish in the 21st century due to the effects of climate change and global warming picking up steam. However, in 2012, he noted that climate change hadn't advanced as rapidly as modelling predictions had stated it would, and he withdrew from this statement. Lovelock himself said he carried on working beyond the age at which he could retire because he was committed to alerting humanity about the impacts of climate change. In 2020, he predicted that the biosphere was in the final 1% of its existence. Getting up to the present day, Lovelock died at home on the day of his 103rd birthday. His Gaia hypothesis remains a very recognizable name in popular science and academia, but, As this episode has hopefully shown, his work was a lot more than just one theory. With that, thank you all for listening. There is more I could have discussed here, such as Lovelock's views on artificial intelligence and how it influenced his views about the future, but given the length of this episode, I will have to leave it here for now. In the meantime, you can get in touch with me at the show's email address for any questions or comments you may have, or if you want to suggest a future topic idea. As always, have a great week, everyone.